a brief summary that what we need to note here is, one, we consider equilibrium of the system before separation. We consider equilibrium of the system before separation, and two, we consider the equilibrium of one of the rods after separation. We usually emphasize that the equilibrium of one of the rods that we consider after separation should be that rod that has the least number of forces. Let me say the rod that is not very clouded. These 2 points are very, very important, and we can quickly take a look at the two. That one, equilibrium before separation. If we have two rods, A, B, C, the rods are AC and BC. They are joined by a string. Usually the strings we consider here are inextensible strings. In other words, these strings cannot increase in length. They have a fixed length. If this rod AC has a weight, say W1, and rod BC has a weight, say W2, then the other forces that will act on these rods will be the reactions at the points where we have the string joining the two rods. And at this point, we'll have a reaction which we can call R subscript B. C is a point where the rods are jointed. And because we have said this is a string, AB, we will have the tension that develops when the string joins the points A and B from both sides. That shows the forces that will act on the system when we have not separated them. Now, here, by taking moments at one point, if we choose to take moments at one point, say A, we obtain the reaction at point B. If we took moments at this point, then we can be able to obtain the reaction at point B. And therefore, this topic requires the candidates or the students to have knowledge on moments. And finally, by resolving vertically, we can be able to get the other reaction. For this particular diagram, I would say in this first part we get RB, and here we are able to get RA if we consider resolving vertically. The second case, when we separate the rods. The second case, when we separate the rods, we change this diagram. This space may not be enough, but I will try to ensure that we look at this. When we separate the rods, this point will be C. I can choose to have one force which we shall call X, one force here which we shall call Y, and then we still have our tension over here, and we still have our weight, W1. Similarly, on this other rod, this is point A, we still have the reaction A, RA. At this point, the forces act in opposite directions. The reason is that the reactions here, the forces we put here should be equal and opposite so that there is no net force at point C. And therefore, our Y on this rod is equal but opposite to this Y, and similarly our X is equal but opposite. We still have our weight, W2, we have our tension here, and we have our reaction at point B, which is still RB. Now, notice that diagram 2, as compared to diagram 1, has introduced new forces that we can call X and Y. It has introduced new forces here, X and Y. How do we determine their value? We can obtain the values of the new reactions by considering equilibrium. This word here is short for equilibrium of one of the rods. Now, this is a summary of what I would call the theory of what we need to be able to do the numbers that we are going to try to look at in this lesson. This question is very common. I'm emphasizing that mainly what we need is knowledge of moments. And for the students that are dabbling as physics students, of course, you will discover that you have an advantage over students that are offering only principal maths without physics. Take note of these. And before we go to our first example, I want to emphasize that if rod AC has a weight as W1, that weight is acting at a point that is halfway the length AC. It is acting at a point that is halfway the length AC. 2, we need to note that we need to know the knowledge of what a moment of force is. And we say a moment of force is the product of the force and its perpendicular distance. A product of the force and its perpendicular distance is what we call the moment of force. I can simply illustrate that, assuming that, just for emphasis, assuming that this angle is alpha. My dear students, hope you're paying attention. I'm illustrating this briefly. And the length of this rod AC is, say, 2L. It would mean that this is L and that is L. In other words, this force, which is the weight, divides that length into 2 equal parts. If this is 2L, then it will be broken down into that. And if we use this angle, then we can be able to find this distance, which will be equivalent to this distance, and this distance is perpendicular to the weight W1. Using trigonometry and taking the cosine of alpha, if this point was called, say, n, you would discover that an would be equivalent to L, the cos of alpha. So we shall be using distances that will be known, but I'm illustrating for purposes of emphasis. I'll request that you take a few minutes, 1 minute or so, to capture this. But at the same time, I request the producer to put the questions, the first example that we are going to use. My dear learners, once again, I request that when the questions are flashed, you could take a picture. We could raise the question a little bit so that part B is clearly visible by the learners. And that is going to be our first example. That is going to be our first example. Capture the question and let us get moving. Capture the question and let us get moving. I want to repeat the topic is jointed rods, and the teacher is Teacher Kakuru. The topic is jointed rods, and the teacher is Teacher Kakuru. I will give you time to copy that number before we can start discussing it. Okay, question 1. Let us focus on question 1. We are looking at examples, and we have the first example right over there. Two important things that you need to take note of. We have said that we have two cases. We have a case where we consider equilibrium before separation and equilibrium after separation. This is equilibrium before separation. This is equilibrium after separation. Now, the question is telling us to find the reactions between the rods and the flow at A and C. And this is point A. This is point B. This is 4 meters. Just keep the question there a bit for me to first pick the information. And this is 8 meters. The 8 meters starts from there and stops there, and the 4 meters starts there. And they are telling us that the rod AB, so if this is AB, B is here. Okay. The rod AB has a mass of 4 grams. So it means it has a weight. My dear students, the weight of AB will act halfway the length. And we don't need this length. For that matter, the weight is going to be 4G. And rod BC has a mass of 6 kilograms. So its weight will act halfway again of BC and the weight is given by mg. Don't be surprised that I'm not writing kilograms. We need to note here that weight is equal to mass times g. And g is a constant which in mathematics is given as 9.8. We are going to be using this. So we can now proceed to the lesson. We can proceed to the solution. Now, the forces acting, fortunately this diagram is still over here. The forces acting include, in addition to the weights, include the reactions. We can let this be Rm and let this be Rc. We can say let Rm and Rc be the reactions at A and C respectively. We have said, my dear students, we have said that once we need a reaction, because they are telling us find the reactions between the rods and the floor when the rope is taut. This is a rope, and this rope will have forces acting. We can choose to call this force, say, FA, and this force, FB. Now we have illustrated all the forces acting. We want to find the reactions, and we are going to take moments. Taking moments at point A, taking moments at point A, it means that if we are taking moments here, I have already said moment of a force is the force times the perpendicular distance. The distances are very clear. I want to emphasize that if this from here to here is 4, and this is a weight of AB, then this distance is 2. And the same applies here. If the weight of BC is 6 grams, then this 8 is divided into 4 and 4. 4 and 4. I hope my learners are following. So if I take moments at A, my 4G, my weight of 4G is going to be acting clockwise. My weight of 6G is going to be acting clockwise. And my reaction of RC is going to act anti-clockwise. And in equilibrium, the clockwise moments are going to be equal to the anti-clockwise moments. I will consider equilibrium straight away and say, okay, if I take clockwise moments alone or resolving towards A in the clockwise direction, 4 will have a perpendicular distance of 2. I'll have 4G times 2. The distance here is 2. The distance for the 6 gram will be starting from here up to there. That is 4 plus 2 plus 2. And it is adding on. 6G times 2 plus 2 plus 4 will give us 8. And in equilibrium, this will eventually be equal to, we can add up this. This is 8 grams plus 48 grams, and this will give us 56 grams. I can call this equation 1. Resolving in the anti-clockwise direction, I'm using arrows. If I resolve in the anti-clockwise direction, I will have only RC. And RC has a total perpendicular distance of the whole of this distance. That is 8 plus 4 times 8 plus 4, and this will give us 12 RC. This can be equation 2. Considering equilibrium, equation 1 would be equated to equation 2, i.e. we are saying clockwise should be equal to anti-clockwise moments. And therefore, we can have our 12 RC being equal to our 56G, implying therefore that our RC is 56 out of 12G. If we reduce this expression, or if we substitute for G, we shall get 56 times 9.8 divided by 12. And when you compute, we can say the reaction at A, at B, at C, which is RC, will be equivalent to, when you compute with your calculator, it should be able to give you approximately 45.733 newtons. 45.733 newtons. That is the reaction at C. Resolving vertically, in other words, considering vertical motion in equilibrium, the forces going up, that is RA plus RC in equilibrium, before we separate the rods, in equilibrium RA plus RC should be equal to the downward sum, 4G plus 6G. So our RA plus RC will give us 10G, and we are interested in finding RA, and we know RC. So I will consider RC at this stage without eliminating the G. Therefore, my RA is going to be 6G minus my RC. If I put in by 4, I'll get 14 out of 3G. If I simplify, this is 18, and that will give me 4G out of 3, which is 4 times 9.8 divided by 3. And when you compute with your calculator, you will be able to get 39.2 divided by 3, which will give you that reaction. Which will give you that reaction as 18. No, this is 10. Sorry. RA becomes 10 minus this. This is 30 minus that. That is 26. 26 times 9.8 out of G will give you, upon computation, the value of RA as 52 point. When you simplify, you get around 52.2, 6 recurring, which you can round off to 7. When we resolve, we obtain the reaction as that. This answers part A of that number. It answers part A of that number. I will request that you quickly capture this because of space on my blackboard. I cannot start on part B. Let us quickly capture this, and remember that for part B, they are saying the body is now attached. Another body is attached a quarter way above CB, and the reactions are equal. For the second part, they are telling us the reactions are equal, and they want us to find the mass of the body. For the second part, they are telling us the reactions are equal, and they want us to find the mass of the body. I will use this same diagram. I'm simply going to update it to suit a second case. I'll update it to suit the second case. So, to suit part B, my diagram, I'm renewing it to suit part B. They are telling us the reactions are equal, so I will use the same letter now. Let the reaction now be R. The distances will remain the same. I can remove the 8 and the 4 since I have these representing them. The weights will remain the same. I have 4G. I also have my 6G. These reactions will remain the same. I can still put them there for illustrating the forces acting. And now they are telling us that a body is attached a quarter way up CB. This is CB. So they are adding a body somewhere here whose mass is not known. We shall let the mass of that body be capital M, G, and I'll put it in writing. Let M be the mass of the body. 2, they are telling us it is put a quarter way. So if this distance CB was known, if it is put a quarter way of the whole distance, it implies that we are interested in finding out what this will be, because this distance is a quarter of the original. So if this is a half and this is 4, a quarter of the 8 is going to be 2. So it is put 2 centimeters away from the hinge C. It is put 2 centimeters away from that hinge. And now they want us to find the mass of this body. To find the mass of this body, M will be unknown. We shall take moments again at point A and then resolve vertically. If we consider either way, we consider resolving vertically first. Vertically means we consider upward forces should be equal to downward forces. And this implies that R plus R, these two, in equilibrium, should be equal to 4G plus 6G plus mg, because the weight of this mass is mg. So that means when we get m, it is going to be in kilograms. Now, it implies, therefore, that our 2r here will be equal to 10 plus m all into g, and we can get the value of r. R here will be r half into 10 plus mg, and we can call this equation A. We can call that equation A. Now, as you notice, if we take moments at A again, we expect to find the value of R. If we take moments at A, we expect to find the value of R, and when we put it here, we can find the value of M. That finishes the interpretation. So taking moments at A, taking moments at point A, we will have 4. We already know how to resolve. What has added in is mg. So we have 4g, 6g, mg all acting in the clockwise direction. Will give us that 4g is multiplied by the distance still of 2. 6g is multiplied by the distance of 8. And now our m, which is here. Remember, it left 2 there, and this was 12. So it will be multiplied by the total, which is 4 plus 4 plus 4. 4 plus 4 plus 4. This is 2. It was divided into 2. Yes, so the 6 is times 8. That is stereo. Is times, if this is 2 and this was 8, yeah. The 6 is times 8. Then the m will be times from here. That is going to be 10. So in equilibrium, there is a g here. It implies that clockwise moments will be 4. This is 8g plus 48g plus 10 mg. We can summarize this as 56 g, 56 plus 10m all into g, and call this B. This is clockwise. Anti-clockwise moments will only be r. The reason we are not taking r, if you are taking moments here, the moment of r about a is 0. Its perpendicular distance is 0. So we will have r times 12. R, the reaction at C, will be multiplied by 12 g. And r times 12. 12 is just the distance. And we can call this C. So in equilibrium, remember that equation B is equal to equation C. But we know the value of R. So we feed it in, and we say that 56 plus 10 m all into G, which is our B, should be equal to R, which we know I'm feeding in R, a half into 10 plus m times G times 12. Times 12. When we simplify, these two will give us a 6 here, and we shall have 56 G plus 10 mg should now be equal to 60, 10 times 6, plus 6m. Plus 6m. They all have a G on them. If we correct like terms, mg with mg and 60 is 56, we shall have 10 mg minus 6 mg, giving us 60 g minus 56 g. 10 minus 6 will give us 4. So 4 mg will also be equal to 4g. So the g will cancel, and we have 4m being equal to 4. Divide by 4, and this will give us our m as 1 kilogram. The value of m will be 1 kilogram. The value of m will be 1 kilogram. They are simple concepts, but they require the candidate to be consistent. The candidate should be consistent with the steps required. As you capture this solution, I will request the producer to move to our second number. I will request the producer to move to our second number as we give 2 minutes for the candidates to capture the solution. Focus on number 2. Candidates out there, learners out there, please take a snapshot so that it is always very important for you to catch up with that question. I will request the producer to move to question 3 and 4, that is the exercise, so that they take pictures only, and then we work through number 2 when they already have the exercise that I expect them to try out. Question 1, as homework, I request you run it up to where they can probably capture the whole of it, if it is possible. There, that's okay. Take a picture. Point B has a 90 degrees. If you notice that triangle for the first homework number, at point B, we should have 90 degrees. Simply take a picture so that you can also focus the next question. And focus the next question, my dear producer. Number 2. Yes. That one. Take a picture, my dear learners. I think that is good enough. We can go back to number 2 under examples so that they can capture the question. I'm sure they are still capturing. That one we can copy, but very fast. We must go through it before this show ends. And now I expect that you actually should be able to go through this number with me confidently. It is almost repeating part of what we looked at, but when we go to the second part, the question requires a little more information. The same thing should happen when you are capturing the solution and you notice that you're not fast enough. Just take a snapshot so that you can catch up later. Number 2, we have steel jointed rods, AB and SC. AB and SC, and notice the point that is being shared is point A. So if they are sharing point A, this time I can sketch, and here they have not sketched for you, like they had done in A. If this is my A is the one being shared, I can let this be B and let that be C. They are saying AB has a weight, and the moment they say it's a weight, we have said it must be acting halfway the length. And also, they are telling us a weight of 10 and length 10 centimeters. Each of weight W and length, so they have the same weight, even this side, because they are saying each of weight and length. And they have the same length, 10 centimeters. And since we have already agreed, without wasting time, that the weight acts halfway the length, then it means that this is 5. They are using centimeters. And this is 5 centimeters. And this would be 5 centimeters. And this would be 5. We have agreed that there will be forces, the reactions they want. We can choose to call this R1 to avoid monotony, and call this R2, because they are saying find the reactions at ends B and C. And they are telling us that the ends B and C rest on a smooth horizontal plane. The plane is smooth. That means we still have the reactions, but we don't have friction. When they mention smooth, it means there is no friction. We can let the tension, which they are actually asking for at the points B and C, be T. And they are telling us that the system is kept in equilibrium in a vertical plane with a string taut. String BC is kept stretched or is under tension. That's what that word means. And they are saying another object of weight 2W climbs the rod AC to a point E such that AE is 8 centimeters. Another object. Now, when we look at another object, they are starting from A. They are such that AE, if we let this object be here, such that this point is E, they are telling us that AE becomes 8, meaning that this becomes 3 and this becomes 2. I hope you are seeing those interpretations. Given that BAC, this angle is 2 theta, but notice that if AB and AC have the same length, this triangle is an isosceles triangle. So if I dropped a perpendicular line here, it would be a perpendicular bisector dividing this angle into theta and theta. Those are the interpretations that we need here. And they want us to find the value of W and determine in terms of W and theta the reactions, R1 and R2. Like I said, it is prudent to take moments on the side that is least congested. So we shall take moments at B. Take moments at B. If we take moments at B, it implies that I have W and W. Now this W, since this is 5 and this angle is theta, we need to look at these distances. its perpendicular distance is this, and if this is theta, it automatically means this is theta. If this is theta, it automatically means this is theta. Using trigonometry, this distance, this one that we need, will be 5, the sine of theta. Let me write them there. And this will also be 5, the sine of theta. This will be 5, the sine of theta. This up to here will also be 3, the sine of, if we look at this, sine of theta is opposite over the hypotenuse, and we are interested in this. So since this is 3, this is 2, this is 3 sine theta, and this is 2 sine theta, because this is also theta. So if we take moments at B, we shall have W times the perpendicular distance, which is 5, the sine of theta, plus W times the perpendicular distance, which is now 15. This plus this plus this, which is now 15, the sine of theta, plus, they told us that this weight is 2W, plus 2W times the perpendicular distance will be from here, 5, 15, 18, times 18, the sine of theta. And in equilibrium, if we look at this, this is 5, 20, plus 36. This will give us 56 W sine theta. I can call this star. Again, if we take the anticlockwise moments, this will be clockwise. The anticlockwise moments will give us R2 times the whole of this distance. And this is going to be 20. It is 20 because it is this 10 and this 10. 20, the sine of theta. And we can call this double star. In equilibrium, we equate these two, and we shall get 20 R2 sine theta is equal to 56 W sine theta. The sine theta cancels, and we are able to get our R2. I think it can fit here as 56 W out of 20, which we can simplify by 4. By 4 we get 1. That is 5. Keep 1. We get 4 out of 5. And this would be W. So the reaction at C is that, which is 14W out of 5. W out of 5. And to find the reaction at B, we resolve vertically. When we resolve vertically, R1 plus R2 should be equal to the sum of the weights. So our R1 plus R2, which is the upward, should be equal to W plus W plus 2W, which is the downward weight. So R1 plus R2 will be equal to 4W. And of course, since we know R2, R1 will become 4W minus 14W out of 5. If we compute by doing fractions, we shall get our R1 as 20W minus 14W, everything over 5. This will give us 6 out of 5W. And we can therefore say the reactions are 6 out of 5W and 14 out of 5W at A, at B, and C, respectively. That answers the first part. That answers the first part. That answers the first part of our question. You realize that our time is first spent, and in the interest of time, I want to quickly interpret the next part. I always don't want to rush as a teacher, because I always tell you that if you rush, you can crash. But I am going to interpret the next part such that even if we don't finish it, you have capacity to finish it, given the time left. It is not so wide. So part B requires us to separate the rods. They want us to find the tensions, so we will use now separating the rods. And the most important part here is drawing the sketch. We shall draw the sketch, and you should not cram that the sketch will always have these forces that way. You can choose here to alternate, that if you have made this going up, what I'm drawing here, you can switch it. What is important is, have you got the concept? We are taking these as the reactions at the hinge A, and we already have the reaction here. My R1 is 6 out of 5 W. My R2 here is 14 out of 5 W. I want to find T. And of course, we have the weights. We have the weights, and here we have two of them. We have W, and we have 2W. And we said we consider the least congested road. Consider the least congested road. I will utilize this space quickly. We are going to consider the road AB. We are going to consider the road AB. If we consider AB, this road here, opposite forces are equal. X will be equal to T. That could be on record. This is horizontal. And also, if we look at vertical, Y plus W, which are all going down, will be equal to the reaction, to 6 out of 5 W. And quickly, we can get our Y. So our Y will definitely be equivalent to 6 out of 5 W minus W. And our Y, as you can see, will give us W out of 5. Our Y is W out of 5. Now we need to want to find X, so we take moments at point B. Taking moments at point B, I'll come here. Moments at B, very quickly, it means I have XY and that W only, and I will say X will be multiplied by the perpendicular distance will be this. Since this angle, this is theta, this will be the cos. So it will be times 10, the cos of theta, plus my Y is going there, the perpendicular distance is this. It is 10 the sine of theta. Y times 10 the sine of theta. And my W is halfway. This is 5 So the distance is this, which means we shall use sine, plus W times 5, the sine of theta. And in equilibrium, these x is anti-clockwise, y and w are clockwise. So I should have an equal sign here. In equilibrium, we have this. If I remove what is common, this is x. X multiplied by, I will divide through by sine. Divide by sine by cos throughout. So I'll have 10x plus 10y tan of theta plus 5w tan of theta. My x, since we know the value of y, will be 1 out of 10 into my x will be 1 out of 10 into 10 times y. My y is w out of 5. The tan of theta plus 5w, the tan of theta. If you compute this, our value of x will be, this is 2 plus this is 7. 7 out of 10, w, the tan of theta. As we wind up the tension, we can conclude and say the tension is equal to x, and therefore is 7 out of 10, w tan theta. And the reaction which they want, finally, the reaction which they want, get it by squaring x and y and take the square root. If you square x and y, take the square root, you will be able to prove that expression. I want to thank you for attending the lesson and want to wish you a very good day. There are 2 numbers that you captured much earlier. Kindly take a snapshot in case you are short of capturing what we have covered. I want to wish you the best. God bless you. Remember to continue reading Gachali Mabaga.
Somera mu ddiiro lyo ng'ewagiddwa Maryland High School erisangibwa Entebbe. Ssomero ly'abawala n'abalenzi tusomesa arts ne sciences okuviira ddala ku siniya esooka okutuukira ddala ku siniya ey'omukaaga nga lisangibwa mu kifo ekiweweevu obulungi. Tulina ebisuula eby'omulembe, science laboratory ssaako ne computer.
Tujjukira ebiseera bye wagendanga mu saloon ew'omuyooyoosi wo n'akuyooyoota n'ovaawo ng'oma